Hi, welcome to Team 43's capstone project. This project is predicting chaos using machine learning. Our mentor is Dr. Ying Cheng Lai.
I'm Danielle Williams.
I'm Matthew Flower.
I'm Rachel Larkins.
I'm Nat Nelbur. So, understanding chaos. Chaos might look random at first, but it actually follows a pattern that are super sensitive to even small changes. A tiny difference at the start can lead to a completely different result. You can actually see these stuff in the weather, power grids, or even heart rate patterns. Because of how unpredictable it is, it's really hard to model, which is why we're using machine learning to try to understand it better.
So some systems that experience chaos in the real world are power grids with distributed renewable sources, also physiological systems such as heart rate and brain waves, and even algorithmic and high-frequency trading systems. What can modeling chaos do? Combined with sensors and data gathering, system parameters can be monitored and critical phase changes can be predicted. This can help predict things like voltage collapse and blackouts, atrial and ventricular fibrillation, and feedback loops in high-frequency trading.
How can chaos be modeled? We are developing a machine learning framework to model four specific chaotic systems. Our first step was to develop the time series data as well as an attractor, which demonstrates both the short and long-term behavior of these systems. Next, we are going to develop a reservoir computer that depends on machine learning to replicate these, these systems, and they will be compared against our ground truth to determine how well we can predict the attractor. Our project goals are to accurately reproduce our input data. This includes both the short and long-term phase states, as well as the chaotic system properties demonstrated in the attractor. Our application is in gathering and implementing real-world data, specifically in areas such as climate, robotics, and control systems.
Challenges of this project include selecting optimal reservoir parameters, managing noisy data and system instability, and then long-term series prediction accuracy. Danielle will handle organization and presentation, while Matthew will be responsible for coding and model development. Rachel will take on simulation and data analysis, and Nathaniel will specialize in systems integration and validation. So who does this project help? Machine learning is being used to perform increasingly advanced tasks. Chaotic and nonlinear dynamics play an important role in many natural and engineered systems. Our project can potentially improve the predictive power of many sensor and feedback systems where chaotic dynamics appear, and then engineers and healthcare professionals will be able to use these systems to predict more events before they happen with better accuracy.
So looking ahead, most models today are either linear or nonlinear, but chaos modeling takes a step further. It's actually more complicated than you think, but it helps us understand systems that normal models cannot. Going forward, this type of modeling could make a big difference in areas like climate, robotics, or energy by helping us predict and control complex systems more accurately.